Paulo Roberto Gomez, Raul Donangela, and Mahir Hussein. And as he said, you start with a weakly bound fragment that can break up or not. If it doesn't break up, it can fuse. If it breaks up, it can fuse sequentially. And by the way, Felipe, Tobias, Federico, and I have expressions for calculating this explicitly, but we've never tried to calculate it and see what comes out. But it can be at least written down. The sequential fusion can be written down in a compact form, just like the other expressions here. But you also have the breakup fusion reaction, where the projectile breaks up, and one of the two fragments fuses with the target, and the other is emitted. And finally, there's the elastic breakup, in which the two particles are emitted. What's interesting is what you can see experimentally. If you look experimentally, you can't distinguish the elastic breakup from the fragments that are emitted with the breakup fusion. So what you have to do is to calculate, if you want to do a calculation, you have to calculate inclusive cross-sections that include the elastic breakup and one of the two fragments that are emitted here. If you look at the compound nucleus emission, however, you have to look at other systems. If you look at the compound nucleus, this compound nucleus, as well as this one, can emit the same particles, and so you have to take all three of those into account if you want to calculate compound nucleus reactions. And so what I want to do here is show you a few examples of both of these using a simplified formalism. What we use is the Ishimura-Alstern-Vincent approach. It's a perturbative approach, which already tells you that it might have some limitations, and we'll get to that before the end, but I want to apply it first. It calculates inclusive cross-sections. For example, here it calculates an inclusive differential proton emission cross-section, and there's a clever reduction that lets you write that as two incoherent terms. The first term is the elastic breakup term, and the second term is everything else, which we'll call the non-elastic breakup. The elastic breakup is a simple post-form DWBA cross-section. In the post-form, you use the usual reduction of the matrix element that puts distortion into the deuteron entrance wave function and into the proton. Well, here I'm talking about the deuteron in particular. This can be extended to other fragmentations, for example, lithium-6, lithium-7, whatever. I'll show some cross-sections for more complicated projectiles in the end. But in this case, the reduction of the interaction lets you put on the distortion into the proton, outgoing neutron, and the incoming deuteron. And so you have a relatively simple DWBA matrix element to calculate. The other term, the breakup term, the non-elastic term, you can write it in a form that you saw in Felipe's presentation as the average value of an imaginary potential. In this case, if we're calculating proton emission, we want to calculate neutron absorption. And so what we have is a wave function, an average absorption cross-section for neutrons, where the neutron wave function is obtained calculating the breakup in which the proton is emitted and the neutron is propagated before it's absorbed. And so it's a very illustrative model in the sense that it lets you see things in terms of a breakup reaction where either the two are emitted or the one that you're not interested in is absorbed by the target. Well, let me say that the theory is old. You can see this goes back, like 40 years. But the calculations are more recent. The Jin Lei and Antonio Mora published an article in 2015, really represented our first calculations in 2014 at the DREB meeting in Darmstadt, but we didn't publish until after. And since then, there's been a workshop at East Lansing where this was discussed in detail, and other things have been done. As far as I know, at the moment, there are 3 people who do these calculations: Antonio Moro and Jin Lei, Gregory Potel in the US, and me, or our group here. Well, just to give you an idea of what happens, this these are typical results. 30 MeV, deuteron 30 MeV on titanium 48 and tantalum 181. In black, you can see the neutron spectrum from the elastic breakup, and the red is the proton spectrum. These are mirrored. The proton, if you turned around, if you flipped the proton spectrum, you see that they're mirrored in such a manner that the energy of the two is always the same. It has to be because it's elastic breakup. So you have to produce as many neutrons as you do protons in the reaction. Here, I've flipped it around so that they're both on the same energy scale here. Oh. And we also see here the inelastic, non-elastic breakup, which is called breakup fusion here, and you see that it's much bigger. This is a general property. Usually the part which is absorbed is much bigger than the breakup fraction. So you see much more of one fragment where the other is absorbed than you do of the two coming out. If you look at the, let's see. Well, anyway, I'm blocking it. Yeah. I still don't see it. There it is. I was blocking it. You see similar results here in the tantalum. And again, you see the two cross-sections with breakup fusion with the neutron being emitted or breakup fusion with the proton being emitted. One of the things that's interesting here is that is not what I expected. I really expected, before I did calculations, that you'd see more protons being emitted than neutrons. It's just the opposite. You see more neutrons than you do protons, which says that the proton absorption is bigger than the neutron absorption. I don't have any really good physical argument for that. It's just an observation that comes out of almost all the calculations. But one of the things that I want to point out here is that you can understand sort of the difference between the peaks in the two if you think of in terms of simple classical physics. When the deuteron comes in, it's slowed down because of the Coulomb interaction. And so at the breakup point, you expect that the deuteron energy, the total deuteron energy is going to be the initial energy minus the Coulomb energy at the breakup point. Well, then after the breakup, the proton accelerates, but the neutron doesn't. And so when they're emitted, you expect the proton energy to have an additional Coulomb energy that it gained from the acceleration that the proton didn't, that the neutron didn't. But that also gives you a means of trying to estimate the radius, the typical breakup radius. If you take the peak and assume that the peak here is the typical radius for breakup, then you can calculate from putting these two together, the difference between the two energies, you can calculate the breakup radius. If you do that for the titanium, we find a breakup radius of about 10.6 femtometers, whereas the interaction radius is about 6 femtometers. If we do it for the tantalum, we find a similar result. It's 14.6 femtometers versus 8.6. So what this seems to say is that although part of the non-elastic breakup could be just a simple stripping to the continuum, to unbound states, there's still a good fraction, at least, according to this calculation and according to these results, that has to be a two-step process, breakup and then fusion. Well, now we can ask, how does this compare to data? Here I take two experiments. One's by Matsuoka. It's an old experiment, fairly old, 1980. And they did a big series of experiments for a big series of nuclei. Here I show the aluminum, nickel, tin, and bismuth. You can see at low energy, for light nuclei, there's a fairly good agreement. It's slightly shifted. The shift probably is in part due to secondary collisions, which reduce the proton energy. But as we go up in mass, we see that there's an increasing discrepancy, at least at forward angles. At backward angles, we see that the calculation is more or less consistent with the experimental data. Well, the backward angles, if you think about it, are usually dominated by the non-elastic breakup part. The elastic breakup is going to tend to go more to the front. So this would suggest that there might be some problems with our elastic breakup calculation here. You can see here the bismuth is really awful. In fact, there's a little bulge here, but one other complication in the case of bismuth is that the additional proton, bismuth is lead-208 plus a proton, and the proton is bound by less than 4 MeV. So there could be proton knockout here as well that we'd have to take into account if we wanted to describe the spectrum well. It's good to see, more recently there have been some experiments that have measured neutron emission, and you see in the case of aluminum that the theory works really well. In copper, there start to be some deviations here that you can see as well that are also not quite as big as they are in the case for protons, but still there's some deviation from between the calculation and the theory. Well, what we want to do is to study how this affects the compound nucleus. These are old calculations. We presented those long ago. The new part of this study is the compound nucleus part. What we do is we use it's an Empire 3 reaction code. It's a code used to study compound or in general reactions involving light particles, neutron, proton, alpha, and it takes into account emission of gammas, neutrons, protons, deuterons, helium-3, and alphas. It calculates pre-equilibrium and equilibrium emission. It includes compound nucleus reactions. It calculates fission. It's a general code used for evaluation purposes. Here, we've integrated the formalism, the breakup formalism into the code. That is, the breakup formalism, if you look differentially, you not only have a distribution of an energy, but you have a distribution in angular momentum. So you have to put in each of the occupations for each of the values of the excitation energy and angular momentum to make a reasonable calculation. And so this is in the code. This gives you an idea of what's in the code. Well, let me just say, overall, if you think of what's happening here, we have the deuteron incident on a nucleus that can fuse as it is. But it can also break up. The proton can fuse and the neutron can leave, or the neutron can fuse with the nucleus and the proton can leave. So instead of one compound nucleus, we have to consider 3. With the calculations we do here, we use the deuteron optical potential. We use a global optical potential for all of the calculations. And so we don't change anything. We just use the mass and charge dependence that's obtained from the global optical potential fit to the mass table. We also don't change any parameters in our calculations, by the way. We fix them and use the same parameters for all of the calculations. The only thing that changed are the optical potentials, but the optical potentials were fit globally to a large number of systems. So what we do is we use the deuteron optical potential here, which is the Hashi-Chen potential that's good up to about 200 MeV to calculate the total reaction cross-section. Here, for people who might not be familiar with this is a plot of the transmission coefficient. So this gives you an idea of what percentage of the incoming flux for each value of the angular momentum was absorbed to form a compound nucleus. Here, almost all of it, it's almost 1. It's about 0.98. Out to an angular momentum of about 28 when it drops down to 0 for larger waves where there's no more fusion. Using the IAV formalism, we can calculate the breakup fusion with neutron emission and with proton emission contributions to the compound nucleus. And here we have 2 compound nuclei. The breakup fusion with neutron emission, you see, is the green curve. The breakup fusion with proton emission is the blue curve. And finally, we can calculate the elastic breakup contribution for each value of the deuteron angular momentum. And you see that this is concentrated on the surface. Although this has a very long tail, which complicates the calculation of the elastic breakup part. The others, the breakup fusion and the complete fusion, are fairly easy to calculate because they're limited in angular momentum to the size of the nucleus. Observe one thing here, which is interesting. As I said before, that the neutron emission is usually bigger than the proton emission. You can see that clearly here, that the neutron emission is about twice the proton emission. So the neutron absorption is about half of the proton absorption in this compound nucleus, which is a curious effect, but it's an effect of the deuteron bringing in one or the other. Note also that they peak at the surface, and we calculate the complete deuteron fusion using subtraction. We don't explicitly calculate the fusion of the deuteron. We just take the total minus the three components here to calculate the deuteron complete fusion, and we see that here it's about 75% of the total. So the effect of the breakup is rather drastic. It takes out 25% of the flux, and it also reduces the deuteron fusion to angular momentum that are more internal. Although the surface concentration isn't complete, there are substantial contributions in the nuclear interior of the breakup fusion. There's still a peak at the surface, which says that the dominant part occurs near the nuclear surface. The breakup entirely near the nuclear surface. Well, so now what can we do with this? One of the first things we want to look at is the D2N reaction. The D2N reaction is interesting because there's a lot of data available because it's of interest for production of radiopharmaceuticals. So deuteron was studied extensively, looking for possible simplified routes for their production. Here, what we have to do, we have to consider two paths for the fusion. One is the complete fusion, where the deuteron combines with the target to form a Z+1, A+2 compound nucleus, which later emits two neutrons. The other path we have to consider is where the deuteron breaks up, emits a neutron, the proton fuses, and then later emits a second neutron. So we want to consider both of these to see what effect this might have on the compound nucleus cross-section. We also want to take a look, if we can, at another question. Remember, I broke up the cross-section into an elastic breakup and a non-elastic breakup. Well, the non-elastic breakup is everything else. It could be inelastic breakup. It could be anything, transfer. And so what we want to do is to have an idea of what else could be included in the cross-section. In particular, for highly deformed nuclei, there could be a big component of inelastic breakup, where although the breakup occurs, the neutron or proton isn't absorbed. It scatters inelastically from the target and isn't observed later. So we've been assuming that it all goes to fusion, and that might not be the case. Well, one of the things, to simplify this, one of the complications of compound nuclear reactions is that when you want to calculate emission, you have an equilibrium process. So what you have to do is you have to calculate ratios of transmission coefficients times final state densities. And the density calculation can complicate things. One of the good things about the D2N reaction is that if we look for heavy nuclei, charged particle emission is suppressed. And the only thing that enters is the neutron emission. Here I have an example here of a neutron plus 208 lead. So this is a compound nucleus without too much angular momentum. This wouldn't be the case if you had a heavy ion on lead. But for a neutron on lead, you see that at low energies, you have pure neutron absorption, and then this begins to decrease at the threshold for 2 neutron emission, which decreases at the threshold for 3 neutron emission, etc., until you get up to a fairly high number of neutrons, with the charged particle emission being suppressed by over 2 orders of magnitude. So one of the interesting things here is that we don't have to worry about the densities. We can just worry about the kinematic factors and the transmission coefficients, the formation factors, if we restrict ourselves to heavy nuclei. Well, when we do that, here's an example of what we find. This is gold. This is data, and okay. thulium, terbium, tellurium, which is a little high here. They're all, in fact, a little high. They're a little high at high energies because the pre-equilibrium component isn't well integrated. We don't have, we have mostly compound nucleus emission. There's also pre-equilibrium emission. If the energy of the incident of the fused neutron or proton here is high enough, there'll be pre-equilibrium emission, which will take out more of the energy all at once and thus reduce the cross-section at high energies. It's something we have to fix. Also, we have zirconium, and yttrium here. These are a little low, but these are all a little high. The heavier ones are all a little high. We compared these superficially with some, using the deformations that are assumed to exist for these nuclei, and we can see that although for the most part there are consistent provisions of very large deformations, there isn't too much that we can see of that's different here. We'd expect if there was a strong inelastic component, we'd expect it to suppress the D2N cross-section. And there seems to be no suppression here, at least as far as we can tell. So there are no systematic effects. So we conclude that at least at first glance, the inelastic contribution is probably not so big. So well, we can go on. Another second interaction I want to discuss is an exclusive dp gamma dpf. What happens here is, what was measured here is a deuteron incident on uranium-238, a heavy nucleus. What they observed then is the proton, they observed the proton and its energy in the outgoing channel in coincidence with gammas or with fission. And with that, they could calculate the ratio, the probability for either fission or gamma emission as the number of coincidence counts for a given proton and proton energy over the total number of protons and the efficiency of detection of the gamma or the fission. Well, what they found is here, I'm going to concentrate on the Ducasse measurement, which is a collaboration between the Bordeaux group and the group at Oslo, and performed at the Oslo cyclotron. And there's an older measurement by Britt and Kramer from Berkeley in the 70, but this is fairly recent. And what they found, there's the Kramer data, and here's the Ducasse data. Two sets, they measured this at two backward angles, 126 degrees and 140 degrees, and found fairly similar results, slightly different, for the proton fusion. And they compared these results with three libraries, three evaluation libraries for neutron-induced reactions. What they did is they take the fission cross-section divided by the reaction cross-section, and you can calculate the fission probability here. That is a function of the neutron energy in this case, or as the function of the uranium-239 excitation energy. And what they found is that their results are much below for fission and much above for gamma emission. They found a substantial greater number of photons than is predicted by the library for the neutron-induced reaction, and a fairly significant decrease in the number of fission events in the same case. Well, if you look here, this is the, just for illustration, this is the inclusive angular distribution for non-elastic breakup, and elastic breakup plus non-elastic breakup as a function of the angle. And these cross-sections here are at 140 degrees and 126, so they're in this region here. You see that the ratio is more or less constant, so it's not surprising that the two cross-sections here are more or less the same as well. Wait, five, so only five? Ooh, okay, so time flies, no? So, but one of the things that's important here is that what they can measure, again, is inclusive proton production. They can't measure the part of the proton production that comes from a fusion reaction. So what they measure here is this solid curve, not the dashed curve, which gives the number of neutrons that really contribute to the fusion cross-section. So what you have to do is you have to reanalyze the data, taking this into account. Well, in order to do that, you have to have a reasonable calculation of the fission. And what we used for this is a recent evaluation, fairly recent evaluation, of the neutron plus uranium-238. Here's data, and here the blue line is the fission cross-section that comes out of that evaluation. And here we look at the compound nucleus cross-section that will contribute to the fission that's of interest to us. Here we see that the deuteron fusion is reduced to less than 70%, whereas the breakup fusion proton cross-section here is about 10% of the total cross-section. Well, when we do that, what we have to do is to use as a function of energy the total proton emission versus the breakup fusion emission. And so what we have to do is rescale the terms that enter this, dividing by this, which is what was observed, and this is what contributes to the compound nucleus. When we do that, we find that we get fairly reasonable agreement. We rescale their data. The black curve is the prediction of the model, and we see that we do a fairly good job of describing their data in this case. What we don't do is a very good job of describing the Kramer data, which even when renormalized still is below the probability for neutron-induced fission, when it should be even bigger than what we do, what we get here. We have no explanation for that. But, well, moving on, the main reason, the main difference is that the deuteron brings in a neutron with more angular momentum. That's why the cross-section gets bigger. The fission cross-section gets bigger. And you can understand, if you have more angular momentum, you turn a little faster, and it's easier to separate. It's easier to fission. You can do a simple calculation. If you normalize the neutron cross-section as a function of angular momentum to the deuteron dp energy distribution, you find something like this. If you compare it to the dp distribution, you see that it's much more extensive in angular momentum. If you do a simple calculation, calculating the average value, you see that at the peak of the dp energy distribution, you have a difference of about a factor of 1.5, more angular momentum brought in by the deuteron than would come in with a neutron alone. What this says is that if you want to do deuteron-induced calculations as surrogate reactions, you have to be careful. You have to do the deuteron calculation explicitly to make sure that everything works out right. Well, you can extend this a little. This is helium-3D. You see, we don't do a bad job here for helium-3 deuteron. However, this is a limiting case here. If you think of, for example, deuterons, okay, but protons, no. Why? Because protons also come from the three-body breakup here. The helium-3 can be 2 protons plus a neutron, and this channel is significant, and so we can't do anything here. What we really need is to extend the model to three-body breakup in order to be able to describe this and many other channels that are of interest to people. You can even do lithium-6 and 7. We're looking at the alpha spectra here, emission spectra. Do a sort of okay job here. Here, one thing that's of interest is that there is a compound nucleus contribution that doesn't exactly solve all the problems between our calculations, but that helps in general with the agreement with the data. There are compound nucleus alphas that have to be taken into account when you do the comparison. And so we can extend this for what it's worth, but the next slide, but there's still an elephant in the room. This isn't everything. It works sort of, but it doesn't work all that well. And as an example, we take the bismuth dp, which you can see works at back angles, but not at forward angles. Well, one of the first things we thought that could be, well, there's a problem with our elastic breakup. However, there's several old works. I think one of the first was by Landau and Lifshitz, where they calculate this analytically. So there's an analytic expression for the elastic breakup, and it's ugly. It's written in terms of hypergeometric functions, but you can calculate it. And we did calculate it, and we found that our elastic breakup is well converged. So the problem isn't there. In addition, if you look at the original paper by Matsuoka and al. And collaborators, you see that they estimate integrated cross-sections. They estimate integrated cross-sections given this, but they have good error bars, so I have nothing against their estimates of the integrated cross-sections. However, you can see that they studied a large number of nuclei, and they really only published about one third of the data. I got into contact with one of the people in the group. Matsuoka's long retired, and I got in touch with somebody in the group, asked about the data, and he said the data retired with Matsuoka. And tell him there's nothing you can do to improve there, but this is something I wanted to say to the experimentalists in the room. If you have data, preserve it. You'll never know when 40 years later somebody might want to use it. Please, take good care of it, make it sure it's in some repository where it can be used by who knows who later. So there's this problem. One of the things that we've seen is that this might be a collective nuclear effect. Some calculations by Fatima showed that the Coulomb part of the CDC calculation compares fairly well with our perturbative calculation, but the nuclear part doesn't. And so it might be necessary really to go to CDC calculations, and that would involve the other. CDC calculations are a truncated three-body problem with one set of Jacobi coordinates. You might have to put in the other two sets of Jacobi coordinates to consider the other two channels. That might be what's necessary here. And I think with that, I'm done. So, thank you.
Well, thank you very much. We have questions. Maybe I can start with a very naive question before Carlos has something more substantial. You showed this uranium fission cross-section. Mm-hmm. Can you go back to that?
Sure.
So why do you have these steps? What's the reason for
the steps?
Yes.
This is first chance fission. The step there is when you can have neutron emission with fission. So it's then the second step is 2n fission. So every step is another neutron being emitted.
So how can we understand that the breakup fusion with proton emission is smaller than with the neutron? How can we understand that?
How can you understand what? I didn't understand your question.
The breakup fusion with proton emission being smaller than...
Good question. If you have an answer, I'd love to hear it.
But there might be some simple explanation. It's not doesn't have to do with the nucleon interaction. Probably it's only the charge I can see, right?
Well, let me say one thing. You notice the difference at low energy. I can't. No, more absorption of protons.
No, you have more emitted protons, isn't it?
No, more emitted neutrons. That's just that's what I would expect. It's just the contrary. One thing is that if you look at low energies, it seems that the neutron can bring in a proton at lower energy than the proton can bring in a neutron. The proton seems to suppress low energy neutron absorption, but the contrary doesn't seem to be the case. I don't understand why. I've checked the code, I've checked the calculations. If somebody, experimentalists, could devise a way to measure that, I'd love to see it, to confirm it. It seems like a very strange result, yeah. Well, I think I'm the only one who noticed. Yeah.
Is it for me now?
Okay. Any other questions or comments?
These calculations, after you have the data, you play with all the parameters, then it's easy.
No, but we didn't play with any parameters.
No, come on. Come
No,
on.
no. We took the parameters from this evaluation,
come
and we
on.
fixed our parameters at the beginning.
People have been doing this for 100 years.
No,
and
no.
They could never
70 years.
Yeah. They could never explain this, and we are still under discussion. So, of course, now you have all this data. You can always play with this optical potential, transmission probabilities, level densities, and whatever. But, you know.
But we didn't play with anything. We took what was given.
Okay. I don't believe it.
Believe me.
There's something that I don't understand. It seems that there is this Coulomb interaction, which is long range, and sometimes it's enough to break up this deuteron. And this very large nuclei, a very dense level system, right? Which energy scale, which can be a few hundred keV or a few tens of keV. Do you have polarization of the target before you have the compound nucleus?
I didn't understand the question. You have?
You can excite the uranium, for example, in this case, can be excited before the deuterium is being absorbed, right?
Yes, it could be, yeah.
Do you take this into account? Is
No.
it important?
No. What we do is we assume that everything goes to fusion. It's either elastic breakup or fusion. That's our assumption.
And you use always the same optical potential?
We use a spherical optical potential, but it's been fit to the elastic scattering. We use the global potentials that have been fit from the 0.23, yeah, I know. It does, I know.
So the
But that's why we looked at the D2N. We thought we might see some effects in the D2N, some suppression due to inelastic scattering. But we didn't see any suppression there, so we assume that, let's say, one of the possibilities is that there is an elastic excitation, but then there's fusion. And so it doesn't really matter if it excites inelastically before it fuses. So we didn't see any real consistent effects of inelastic scattering. We'd have to do a more elaborate calculation than we've done so far to do that. Yeah. But it should be there. Yeah, I agree.
Okay, I don't see any more questions, so let's thank Brett and Felipe again for their talks. And then we will meet after the lunch break at 2 p.m.